very suitable for this kind of applications. Wim has held positions here, the ABS chair, the Doherty chair. He has taken awards from the Army and to develop his career. He has several awards. So, without further ado, Wim.
Thank you, Michael. Thanks for the introduction, and thank you all for coming. I understand it's non-trivial on a cold Friday at the end of the term, so I'm very grateful that you choose to spend the next hour here listening to me. So I'm going to talk about a big part of my research, not everything, but this involves the high-order simulation methods, and I'm put forward an inverse fluid structure interactions because these are sort of the two sections of my talk. Forward for me is the simulation. So, what does the flow look like given some body and flow parameters? And then inverse is about the design and the control. And so my outline will be sort of split in those two parts, where the forward problem is going to be sort of talking about immersed discretization of partial differential equations, and then also going to 3D on adaptive grids. So this is both sort of the forward problem, and then the inverse will be using data-driven surrogate models. Okay, so let's start with the immersed discretization and why do we sort of choose to develop this method. And so as Michael said, broadly, I'm interested in problems that are sort of have some key characteristics. So the vortical flows, these are high Reynolds number problems. So there's a sort of strong nonlinear behavior. 3D effects are generally important because either the geometry is three-dimensional or the flow becomes three-dimensional at these high Reynolds numbers. And so we have to resolve the three-dimensional effect. Often characterized by moving and deforming boundaries or interfaces, and also scale separation. So if you have flow past the body, you have a boundary layer where you need very fine resolutions, and then a weight where you can be coarser, and then sort of far field where you can be even coarser. And so if you're in 3D, you want to take all the advantages you can get in terms of computational efficiency. And so we want to account for that as well. And then there's also often multi-physics problems. So we want to think about fluid structure interaction, multi-phase flows, hydroacoustic things that couple different physics across different domains. And so we want to think about those things when we develop our method as well. So within this broad category of problems, immersed methods have created a lot of new capabilities, and it's a popular method in academia, some also more and more in commercial and sort of practical solvers over the last few decades. But they are typically characterized sort of universally by a low order of accuracy, and I argue that poses a ceiling in terms of what they can achieve in terms of performance and accuracy. So just as a step back, what's an immersed method? So traditionally, when you do CFD, you would create a grid around your geometry. So you have a computational domain. This is the square, and then a body, the yellow, and you create a grid around that body. You can spend a lot of time fine-tuning the grid. Everyone that used OpenFOAM has created a grid at some point. And that works very well after you create the grid. But once the body is doing sort of complicated stuff like moving or deforming, you have to do something, and you have to update your grid dynamically, which is sort of expensive. And if this body starts rotating, then it becomes impossible, right? So you have to redo your grid on the fly adaptively. And so these type of methods are sort of, they are very accurate when you have the grid, but they're very hard to maintain when you have things that are moving and deforming. So mesh generation and adaptation is expensive and possibly very, very complex. So the immersed method is sort of the opposite, where you have a body that is described, the geometry of the body is described independently from the grid, right? So we have a background structured grid, so we don't need to mesh, and the body sits sort of on top of that, and we deal with the body in the discretization. We can further sort of distinguish between two classes. Traditionally, the immersed boundary method puts a sort of a smooth delta or heaviside function near the interface, and that causes a continuous forcing method, a modified interface, where you slowly go from fluid to solid over a series of a couple of grid points. Those methods are sort of the early immersed boundary methods, very easy to implement, very robust, difficult to extend to high order. Second is hard, higher than second is very hard, but widely used because of their robustness and simplicity. If you want to go sort of more accurate and more fidelity, you have to think about discrete forcing methods, and these are sharp interface methods where you would locally change your discretization scheme according to what the body, where the body is exactly, right? So you have these sort of intersection points where the body crosses the grid, and you would change your discretization scheme on those locations. So this is essentially creating a sort of a body-fitted grid on the fly, right? And what that can do is basically extend to high order. You can resolve quantities that live on the boundary, but it's challenging to implement, especially when you go for higher order accuracy. And there's some examples in literature, like the sharp interface immersed boundary, cut cell finite volume, and also the immersed interface method. So why do we think about going higher than sort of second order? Sort of well known in CFD is that when you apply high order schemes to smooth problems, including incompressible fluid flows, you have reduced dissipation and dispersion. So you get higher accuracy per computational element. And at the same time, the typical discrete forcing methods are still at most second order accurate. So that whatever sort of flavor of method you pick, there's very little that go higher than second order. And these low order methods work well if you have enough resolution, but once you go to sort of high Reynolds number flow, you can miss important flow structures, make spurious errors, unless you refine sort of excessively fine, right? And so examples are sort of the long time evolution of wakes, or if flow vortex-vortex interactions where nonlinearities can cause errors that accumulate. And for that reason, we're not the only one that think about high order immersed methods. There's a bunch of work over the last 10 years or so that has really sort of increased. And that spans all the type of flavors of method that you can think of. So from finite difference to finite volume to discontinuous colloquing, or even going towards spectral method. So we're all thinking about trying to get more accuracy for our given computational grid, and by extension being more efficient. But of course, there's challenges. Broadly, these methods are not as robust as low order methods, so they limit their current use in applications. So what we try to do is develop a high order immersed method that has high order space and temporal discretization errors on static and moving immersed domains, but at the same time stay robust to geometries in 2D and 3D, and also have a sort of a generic application to PDE and boundary and interface conditions. Okay, so we start from an immersed interface method, which is a classical method from already a couple decades ago, that was developed to tackle finite differences with jump at immersed interfaces. So here's a 1D grid. The xi's are the grid points. This x alpha is an immersed boundary, so it sits between grid points. And we have a function that lives on one side, a function that lives on the other side, and at the interface we have maybe a jump condition. So this can be fluid flow with an elastic membrane in between at x alpha. And so if we apply a finite difference scheme, we're in trouble because xi plus 1 for xi is not giving me a correct sort of right point. And so what we have to do is correct the finite difference scheme, and the classical immersed interface method uses jump corrections to correct the finite difference scheme. So from the perspective of the left function, the right neighbor becomes a standard Taylor expansion plus some corrections, and the corrections use the conditions at the interface. So what we did was reformulate it a little bit so we can be more generic to different types of boundary conditions, and essentially show that it's equivalent to reformulate this as a polynomial extrapolation, where you essentially construct a polynomial through your field values, including the boundary, and then extend that out. And once you have that ghost point, you apply a standard sort of finite difference scheme on the extended field. So this is a very generic idea. Our perspective is slightly different because we come from the immersed interface side, but broadly there's a similarity here with sharp immersed boundary methods, ghost fluid methods, and other type of techniques. Okay. So when we take that paradigm and try to extend it to high order, there's some challenges that show up. And I list the sort of most obvious ones. One is the extension to more than one dimension. So here's an example where we have a concave geometry, and if I try to create my polynomial, I don't have enough points to the left because one of them falls outside of the body. So I cannot create a high enough order polynomial given these extensions. Conditioning might be a problem because we might try to form a polynomial where a grid point sits very close to my boundary point, right? The boundary point can be anywhere on the grid. And so that leads to an ill-posed polynomial formulation. Stability for hyperbolic PDE is an issue. And that's because when we try to apply an upwind scheme at an inflow boundary condition, we essentially extrapolate downstream into the ghost part of the domain and then use an upstream finite difference tensor. And so that becomes inherently sort of unstable. You can show that formally that if we could try to go higher than third order accuracy, you are unconditionally unstable. Moving boundaries and high order time integration is another challenge. So let's say you do everything nice in space, and now you want to go high order in time, and you have a moving boundary. Now you have points here that emerge over time, and you don't have a time history in those points. So you cannot apply your standard high order Werner-Kutta scheme you need to fill in a time history at any substep that a point gets uncovered. Treatment of complex boundary conditions. So if you want to apply this in real life problems, we have to tackle complex boundary conditions. For instance, in elasticity, we might have an imposed traction, and the traction couples derivatives of the displacement fields all together at a single point. And so if we want to create an extension of the displacement field, we have to sort of couple all the components together across this interface to create the appropriate ghost values for every displacement component. And lastly, all of these sort of 5 challenges are agnostic to 2 and 3D. Right? So if we solve it in 2D, we can directly apply it in 3D. There's one problem specific to 3D, and that's the scale of the problem doesn't allow us to use direct solvers anymore for inverting linear systems. So if we have an elliptic partial differential equation and we want to do that in 3D, we have to think about robust and efficient linear solvers, specifically on the large scale problems of 3D domains. So I won't talk about all of our work in this realm, but I'll give you one slide on sort of the general approach that we take to tackle most of these in sort of one shot. And the idea is to use a weighted least squares polynomial. So instead of using 1D schemes, like I showed on my first slide, when we go to 2 and 3D, we use weighted least squares polynomials. And so what that allows us is a sort of geometric robustness, because if points fall outside of the domain, but inside of our stencil, we just exclude it. And we choose our stencil large enough so that we always have enough points for the given order polynomial that we need. So we can apply these, we can construct these least squares polynomials at every one of these control points and then use them to fill in ghost points and then apply standard finite difference schemes on the domain. And the polynomial here, the ghost point is evaluated from a polynomial, which essentially boils down to a set of linear combinations of domain values with appropriate coefficients and a boundary condition with an appropriate coefficient. And so that's also linear operations that you can apply very, very rapidly. And then after we compute the ghost points, and we might have to fill in a bunch of them, like 2 or 3, depending on the order of the finite difference stencil, we can use standard dimension split high order finite difference techniques. So what that gives us, and we can extend that immediately to immersed interfaces. So this is a boundary. If we have an interface with physics on both sides, we can create these regions on either side and couple them across that control point, across that interface point. And that's independent for every one of these intersection points along the boundary. So that's highly parallel. So what that gives us is a bunch of benefits. We can do high order. So we can choose our polynomial order arbitrarily high. We can handle we can be robust to geometry. So if there's concave geometries, we can choose a large enough least squares region so that we always have enough points to form a polynomial. It's well conditioned because we simply remove the first point from the stencil. We can handle non-Dirichlet boundary conditions, so we can solve a small system of equations for the ball value prior to applying this formula. If we have, for instance, a traction boundary condition that couples all the components, and then we get all the wall values that we need to essentially enforce the traction condition, and then pretend it's a Dirichlet boundary condition. The weighted least squares, the weight part is important because it allows us to emphasize points closer to the interface more than points farther from the interface. And what that does is it gives you stability for hyperbolic PDEs, so that the downstream-upstream problem is partially solved by using weighted least squares. And everything in the end is a linear operation, right? So all the operations are linear in the field values, unless for some reason the boundary condition itself is not linear, then we cannot avoid. So let me give you some examples of where we use these methods or what we apply them to. And it's sort of, I think, beyond most of this is sort of complexity that I haven't seen much in literature. So here's a linear elastic problem, very generically posed, where we have a body force, we solve for the displacement, and we might have different types of boundary condition, like displacement, traction, a jump in the displacement and the traction. And so you have a Dirichlet, Neumann, and a material interface sort of boundary. And we discretize all of this with our immersed stencil. So we always use Cartesian grids, represent the geometry on that Cartesian grid in whatever manner you'd like. No worry about body fitted meshes. And we can show that we achieve up to 6th order errors on the solution, both in the domain and on the immersed boundary. And we can handle displacement stress, continuity conditions. We can have flexibility to non-homogeneous and anisotropic materials in the domain. And so as an example, we typically use manufactured solutions because we have an exact solution ready to go, so we can compute errors. And here's a plot of the infinity error for this problem. So we have here a Dirichlet on the outer boundary and then a jump condition on the interface where we prescribe the displacement and the traction. And what this infinity norm errors gives you is the maximum error everywhere in the domain. So including points very close, arbitrarily close to the interface. That says the maximum infinite norm of the error. And this shows fourth and sixth order for different types of discretizations, different order polynomials, both on the solutions on the interior as well as on the boundary. So here we resolve the traction, the displacement on the inner part of the interface, right? And that gives me still sixth order accuracy. And then we extend this all to nonlinear elasticity, where we now put a Saint-Venant-Kirchhoff material on the inside, Neo-Hookean on the outside, and again get high order convergence on the displacement and the traction using this formulation. So it's sort of an alternative to some of the immersed finite element methods that exist. This is purely finite difference and still achieves higher order than many of those finite element methods can achieve without having to do any sort of quadrature, right? So we don't have to account even for the curvature of the interface. It's purely based on intersections and normals. And so Carlos helped us come up with a sort of a complex problem. This is a honeycomb lattice with defects. And Carlos and Andrew Chan, his student. We apply our method to this problem. There's a zero displacement on the bottom and imposed shear at the top, traction free at the sides. Those are the boundary conditions on the outside. And on the inside, we put an infill material. So we have a jump in stiffness between the material in the voids and the material in the lattice in these little rods. And so we compute the von Mises stress using our methods, and we compare with Abacus, an embedded finite element solver. And here's some close-up of like one little rod in this entire sort of domain. And it's very hard to see any difference between these two methods. And so what that shows us is that we can get high fidelity, right? We can results comparable to commercial solvers without having to create a mesh, right? So we never have to create actual body-fitted meshes. And so if we would change the geometry, it's really parametrically formulated, right? We can do any sort of parametrically geometry, just run it through the solver without manual intervention. And quantitatively, if we take a slice through this domain, we can plot the von Mises stress across this line. And what you see is if you zoom in, you see the jumps in the stress. It's we're fourth order accurate in the infinity norm, and we still have sort of sharply resolved jumps whenever we switch from one material to the other, where the black line here is our result, right? So that's the sharp jump. And the embedded finite element method does not resolve the jumps sharply there. So that's immersed methods applied to elasticity. We want to go to Navier-Stokes as well. So we also worked on the incompressible Navier-Stokes equations. We did a couple of small variations to what I talked about before. One is that Nigel, my student, developed a way to do fifth order stable hyperbolic PDEs. So we have a fifth order upwind scheme, fourth order central scheme. So we're nominally fourth order everywhere. And we have a small modification to the boundary condition of the pressure Poisson equation that allows us to get high order in both the velocity, but also the pressure. And so as a manufactured solution, again, we have a Taylor-Green vortex with a star that's sort of rotating around. So it's moving across the domain. And putting everything together gives us, at the highest discretization that we can achieve, a fifth order convergence and a fourth order pressure in the infinity norm. Right. So we are sort of beyond what most of the state of the art can achieve, which is second order for both in the best case scenario. Although people usually don't show the infinity norm. So there might be some exceptions to that. And just to show you what that does is here's a problem that I took from the spectral method literature, which is a vortex dipole wall collision at Reynolds number 1,000. So this has been benchmarked quite a bit for spectral problems. But spectral method uses simple symbols or squares, unit squares, and so the vortex hits one of the sort of domain-aligned boundaries. So what I did was put the domain at an angle. So my immersed boundaries are always at an angle with respect to the grid line. So it's a very awkward problem, but it really stresses our immersed discretization because as this vortex hits the wall, the whole flow evolution is driven by the vorticity generated at the wall. And so when we run this with our fourth order method, we get a nice evolution of the flow. Again, this is the immersed boundary, this is the grid boundary. So we only solve in this immersed domain. It's sharp, there's no sort of leakage or anything like that. And if we compare with the spectral method, we see that the fourth order results sort of overlaps on the spectral results, whereas the second order version of our method has some large differences at this inner vorticity being generated. And if you run for longer, that will sort of mess up the whole solution. So here in red is the spectral results, and in black is our results. And of course, if we go high enough in resolution, the second order will get there eventually, but this needs about 3 to 4 times more points. And as you increase the resolution, you also need to decrease the time step because of the CFL condition, so that sort of cascades down into higher cost. So ultimately, it's about a 10x computational improvement for the fourth order method compared to the second order one. And then as the truth test, we can look at the wall vorticity along the immersed boundary. And so the wall vorticity is the gradient of the tangential velocity, normal gradient of the tangential velocity along this immersed boundary that does not align with the grid. And what we find is that our fourth order results in red overlap with the spectral results of a wall-aligned wall-aligned domain boundary. And so that's something that I haven't seen immersed methods achieve. So the level of fidelity here at the computational relative to the computational cost is extremely high. Okay, so that's 2D Navier-Stokes. If we want to go to 3D, I said there's one issue, which is how do we solve the 3D elliptic problem? This is a paper I can talk for a long time about that, but basically when we have an elliptic PDE, like a Poisson equation or a Laplace equation, we have something like this, where the del square U is equal to F, and then a Neumann boundary condition or a Dirichlet boundary condition on an immersed boundary. After we do the IAM discretization, what this gives is essentially a big linear system where we have the free space discretization stencil as if there's no boundary, and then we have some local corrections that both apply to the solution and to the boundary condition vector. And so in the end, we put this boundary condition term to the right-hand side, and then we have a free space matrix plus a low-rank correction for the IAM corrections. So we have a near interface correction to the free space steps. So we end up with a big sparse linear system of equations that we need to solve, and we cannot invert that directly. So our goal was to construct an iterative solver with an effective preconditioner, because this is ill-conditioned, that is matrix-free, so we don't have to formulate the whole matrix, which is relevant because we want to apply this to 3D adaptive grids, and is also robust to the immersed geometry. So we can resolve this with complex sort of geometries immersed on that domain. And our solution has been, it's taken a while, but we ended up on sort of a 2 different discretization approach. We have a GEMRIS that is solving the original high-order discretization. So all the fourth order IAM bells and whistles and all the high order finite-difference stencil on the final grid, on the finest grid, are solved using a GEMRIS. And then as a preconditioner, we use a low order stencil that is extremely robust to geometry, to the point that we can have one point inside a body and it's still going to be fine. And that preconditioner is solved using a geometric multigrid method, which we now can do because this stencil is so robust to geometry. So we can go and coarsen the grid in the multigrid hierarchy and solve this all the way up and down. And so that gives us the ability to solve large-scale 3D problems, 3D elliptic problems, to second, fourth, or sixth order accuracy. Those are those 4 lines with either Dirichlet or Neumann boundary condition. And here's a manufactured problem inside a immersed convex concave boundary. And crucially, the number of iterations that we need in the GEMRIS solver is roughly constant with resolution. Right? So the low order stencil is an effective conditioner for the high order technique. So what that gives us is up to 6th order convergence for both Dirichlet and Neumann boundary condition. Number of iterations roughly constant. This works on adaptive grids. And the implementation is massively parallel. So we scaled this all the way up to 32,000 compute cores on a supercomputer, and we maintain about 95% efficiency in the weak scaling. So that gives us the ability to tackle large-scale problems, and it sort of solves the last problem of our immersed method. And my visiting student, Andrea Paris, wanted to apply this to something fun, so he solved the potential flow, which is essentially a Laplace equation with a Neumann boundary condition, past a cow. And so there's a graphics model from Keenan Crane that is called Spot, and the graphics people do all sorts of horrible things to Spot. And we just decided to run the flow path spot potential flow, and these are the surface streamlines over the surface and the actual free space streamlines. So physically, this is sort of not so interesting, but numerically, this is actually a big problem. This is if we wouldn't adapt, this would be a 3,000 cube computational domain. With the adaptation, we are left with about half a billion points, 5 million surface mass intersection, fully fourth order, and solved on 2,000 compute cores of a supercomputer. So we can tackle some large-scale problems with very complex geometries to high order without ever having to worry about creating a body-fitted grid. So our solutions to high-order methods are essentially summarized here. Least squares solves a bunch of these things. So the extension to high dimensions, conditioning, and the weights in the least squares solve stability for hyperbolic PDEs. I didn't show you our work, but we derived and analyzed an exposition-based time history approach for emerging points, so we can also get high-order time integration. We have found an effective way to incorporate complex boundary condition, which is basically solve a linear local system of equations for every control point that gives you the Dirichlet boundary condition that you need to move forward. And we have developed a well-conditioned 3D linear solver for high-order immersed method with massively parallel scalability. And so with that, we're sort of ready to go to 3D. The one piece is the adaptivity. I won't talk too much about it, but I'll give you a brief sort of summary of what we did on that end, which is largely orthogonal to the immersed method. It's basically how to develop adaptive grid methods with high order. The goal of that sort of branch of research is to exploit spatiotemporal scale separations with efficient high order adaptive schemes. Challenges are coming up with effective indicators, so deciding when to refine, when to coarsen, doing the actual refinement and coarsening in a sort of way that is consistent with your discretization, performing actual discretization on multi-level grids. So how do you compute ghost points if your neighbor is finer or coarser than you are? And in 3D, we want to do this in a parallel load balance way. There's some high-order existing work on high-order adaptive grids, such as in the spectral element community, discontinuous lurking, contact finite-difference, also some wavelet work. That's what we do as well. And finite volume has a long history of adaptive mesh refinement. Our approach uses a wavelet collocation approach, and what really sort of stands out here is the sort of consistency with the finite difference scheme, and also the being able to go all the way up to sixth order wavelets to get fourth order accurate. And so the implementation, we call it Murphy. It stands for multi-resolution, multi-physics. Thomas Julius, my postdoc, developed all the foundation of that. And it basically combines a few things. We use interpolating wavelets for multi-resolution analysis of the field at any point in time. That allows us to represent the function to high order on an adaptive grid and from consistent compression refinement. It's all based on the wavelet analysis. And also the wavelet gives us ghost point for our finite difference key. The implementation works on a block-structured octree grid. So we can have these little blocks that always have the same number of points, but they exist on different physical levels, and they're all organized in an octree grid that allows us to do some load balancing and have nice access patterns and vectorize the performance. And throughout, we use high-order finite difference for advancing the equation in each block. So very briefly, the adaptation strategy that we use, which is every sort of 10 time steps, we reanalyze the field and change the grid that we needed. We first perform whatever order you want, enter the interpolating wavelet transform of the fields, compare the maximum and minimum detail coefficients in each block with some thresholds that Nigel recently showed my student has, but you can prove that in linear PDEs, those thresholds actually bound the error of the PDE. Once you compare that, you refine and compress accordingly. And finally, we have a new grid and we advance and solve the PDE on the new grid. So with that, we can do some adaptive grid simulations. Here's a sort of a standard benchmark, a Taylor green vortex at Reynolds number 1000, where the grid is sort of adapting on undefined features. And our collaborators in Belgium, who've taken our framework and put in a vortex particle method on top of that, they've recently simulated vortex ring collisions at Reynolds number 7000, where the adaptivity is all handled by our framework. And these simulations were done on up to 8,000 cores. And they calculated if they wanted to have a fine uniform grid of the finest resolution, they would sort of exhaust all the clusters on their supercomputer, all the cores on their supercomputer, which itself is top 5 in the world. So they get massive compression ratios because of the adaptivity, and especially for problems like this with large scale separations in space and time, that helps. So what we did is take this framework and put all our immersed method discretization in there. And so now we have sort of a bingo of keywords. We have a 3D high order, adaptivity, and immersed, all within one solver. And so when we solve some problems like flow past a sphere, this is a benchmark that everyone has done that does some 3D solver development. We can get good results compared to literature in terms of the forces and the lift RMS. But our highest linear resolution is 2 times or more coarser compared to most references. And so when we take the linear resolution and cube it because we're in 3D, and then add 1 more power because we are CFL bound, that gives you a 16 to 20x sort of reduction in the spatial temporal degrees of freedom to simulate from time 1 to time 2. And then on top of that, we get about 30x reduction from the adaptivity. So this is sort of where we are. We are exploring some applications and some further test cases. Xinjie, my student, is running some very complex simulations where we try to at the same time benchmark and push the solver a little bit. This is flow past a sphere at Reynolds number close to 4,000. The effective resolution is 87 billion points, but then we compress it, so the rate on the adaptive grid, we have about 1,000 to 4,000 fewer grid points. There's a reference result where they ran on 32,000 cores this same problem, and we run it on 2 nodes of a supercomputer, so 256 cores. So the compression and the high order together get you all this savings. And then we can also do moving boundaries. So now this is a pitching plate, so a plate that is dynamically pitching up. It's very thin, so we really stress the resolution. It's 32 times thinner than the chord. We have 300 points along the chord. And this simulation would be 500 billion points, which would certainly be up there with the largest CFDs. Effective resolution, but we massively compress it because of the adaptivity, and we can run it only on 4 nodes, 512 cores. And of course, these compression rates are somewhat artificial, right? If we make our domain larger, we get larger compression rates. But still, these are problems with very, very fine resolutions, and still we need large domains to capture the whole flow. And so the adaptivity is crucial in that. Okay, so on the immersed methods and the adaptive grids, we combine high-order adaptivity and massive parallelism for unprecedented complexity simulations of large-scale 3D vertical flows with moving boundaries. Sort of hand-wavingly, the high order gets us about 10x, order 10 reduction in spatial temporal degrees of freedom, more in 3D than in 2D. And the adaptivity in 3D gets us, depending on how, how large the scale separation is, 2 to 4 orders of magnitude reduction. And so this is now can directly be applied to high-fidelity vortex moving body interaction problems. And we have some immediate development work ongoing to sort of 2-way coupling, FSI, and further 3D performance analysis. And where we want to go in the future is extend this to further multi-physics problems. So we got some funding to study free surface flows. We're also interested in solid mechanics from an Eulerian perspective to do FSI, large ID simulation, and other type of things that exploit really the ability to handle complex problems, multi-physics, interface-coupled multi-physics problems, and sort of complex boundary conditions. And also we want to, on the adaptivity side, think more about how to combine adaptivity with LES and subgrid scale models to integrate sort of multi-fidelity data-driven training pipelines for LES with adaptive grids. Okay, so that's on the forward problem. So let me talk a little bit about what we do on the inverse side, where this is still in progress. So this is something I'm excited about, but not necessarily at the end point. And that's tackling inverse problems using data-driven surrogate models. And so the motivation here is that any problem that involves flexible or morphing structures, whether it's sort of aerodynamics or underwater locomotion or sort of multimodal locomotion, you would have a bunch of challenges in the design. And that is because So the structural design, so how you distribute your flexibility and the control, and the fluids all sort of wrap together into this very complex forward problem. And so the inverse problem is going to be hard to solve comprehensively, right? And so on top of that, your structural design might have very high dimensional degrees of freedom, because maybe you can change your compliance continuously along a dimension. You might have high dimensional actuation degrees of freedom because you have smart morphing structures. And in the end, your performance arises from this interplay between flow, structure, and actuation, where the flow is the really critical part, because it couples everything in a very complex nonlinear way and makes it hard to extract reduced order models. And because of that, if you do a naive FSI optimization, which is essentially throwing experiments or simulations at the problem, that becomes intractable, just because the complexity in the parameter space is too high dimensional. So what we've been exploring, starting with a conference paper a couple of years ago, was to derive a surrogate model that can approximate the shape load operator. And what I mean with that is that if I have the FSI problem sort of sketched out in several steps, we would have a structural solver that determines the shape of the structure, and the flow solver determines the loading on the surface, and that feeds back into the structural solver. So the coupling between the flow and the structure always happens on the surface of the body, right? The shape feeds into the boundary conditions for the flow, and the flow loading, the aerodynamic loading or hydrodynamic loading, feeds into the structural model. And once you know that surface field, one domain doesn't care about what the other domain does, right? All the coupling is really on the surface. And this thing might have, parameterized by high-dimensional structural design space, flow conditions, to maybe an actuation going on as well. And all of that together leads to the aerodynamic performance. So what I'm interested in is to develop a surrogate model that can abstract out this part. So the complex part, the expensive part numerically or experimentally, which is the flow solver. So can I find a surrogate model that goes from shape to loading? And so then I can solve the whole FSI pipeline without having to run more simulations. So the idea is to learn a shape loading map using a surrogate model trained on CFD data, which can be rigid, right? It can be sort of imposed one-way coupled FSI. And then once you have that model, evaluate or optimize any structure actuation design using only that model and everything going on the structural side. So we did a first implementation in this paper where we just look at a very simple sort of proof of concept approach where we used a hinged airfoil. And so the shape here, this sort of part of the surrogate model, is just a vector of angles. And then if you run this to a solver, we used Xfoil because it was cheap and we could validate sort of the surrogate model with the real thing. That would give you the aerodynamic torques on these hinges. So that's the loading. And then you can put some hinge stiffnesses, some torsion springs or some rest angles or other complex sort of flexible compliance elements to go back to the shape once you have the torques, right? And so you can iterate this through equilibrium if this is a steady state problem. And once you trained your model on the shape loading map from Xfoil data, you can run all of this without further CFD evaluation, without further Xfoil evaluation. So if we want to extend this to transient problems, to problems that are time dependent, we cannot use that same sort of paradigm anymore. And so I've been thinking about this from the perspective of a very simplified problem, which is a heaving foil with a single hinge. And so here's my foil. It's moving up and down in 2D. There's a single hinge that sits at 60% of the chord, and this trailing flap here is moving up and down. So this hinge can be compliant. The heave motion is imposed. The parameters that are fixed are the Reynolds number of the flow, the amplitude of the heave motion, and the Strual numbers. And from a sort of rigid body or from a force perspective, the only things that are relevant here are that the shape is described by this angle, which varies over time. And the relevant forces are the torque from the hydrodynamics on this hinge, as well as the lift and the drag force on this body. And so what we want to achieve now is try to find out if we can learn a surrogate model that predicts for us these three forces, or the two forces and the torque, given a time history of the kinematics of both the hinge and the heave together, right? And so there's some theoretical basis for why a partially observable system would need sort of a time history. But because we don't have a closed form PDE that links these kinematics to the forces, we have to use a time history. And so we just take a network, an LSTM machine learning approach, because we've worked with that in the past, and it's sort of proof of concept here. So we take an LSTM and take a time history of this kinematics vector, run it through a fully connected network, and that would predict for us these two forces and the torque. So the input is the time history of heave amplitude and hinge angle, and the output is the forces and the torque on the hinge. And we train that using CFD simulations, where we impose this angle over time. So we impose alpha harmonically in this case, with amplitudes in a certain range, frequencies relative to the heave frequency in another range, and all the phase angles that are possible. And we vary those three parameters, run CFDs, and use those relation between the alpha history and the force history to train this network. The training data here consists of about 100-something simulations, about 500 cycles. And we use our in-house CFD solver based on the immersed interface discretization to quickly run these sort of in an automatic fashion. And once we have that model, the structural ODE really becomes only this form. So the equation for the alpha in an FSI setting would be sort of an inertial component here with the moment of inertia. This is because we're in a moving frame of reference, so we account for the heave acceleration. And then on the right-hand side, we have everything that forces it. So that's the hydrodynamic torque, which we learned, and then potentially maybe a spring, maybe we have a torsion spring or a damping term, and maybe also an actuation that is a motor that sits in that hinge and drives the hinge angle. So as a structure actuation inverse problem, we have everything here to optimize. But now if we trained the model to learn the hydrodynamic torque from the alpha history, we can run this entire thing offline, right? And so we can solve this simple ODE offline without further CFD and choose any parameter combination out of this vector that we want and predict what will be the forces on this body. So we solve this little ODE scalar using an RK2 time integration and evaluate thrust coefficients, power coefficients, which includes potential actuation that is applied to this hinge, and fluid efficiency. And here the torque comes from the model, and as well the lift and the thrust force. So we run some comparisons between what the model predicts for a given varying the spring stiffness of this hinge. So here we fix the damping and inertia and everything else. We vary the spring stiffness and we predict the thrust from the model and then validate it with CFD. And then the same for the power and the same for the efficiency. And we get a good sort of correspondence between what the model predicts in 10 seconds and what the CFD predicts in an hour or two. And here's some examples of what happens if the spring is sort of on the softer side and on the stiffer side. So with this model, we can run the fully multi-objective optimization without sort of batting an eye, right? So we can evaluate about 5 to 10 of these evaluations per minute. So in about 24 hours, we've done 10,000 parameter combinations, and we can run this in a simple genetic multi-objective optimization loop to optimize things. So here's where I optimize for the purely passive deformation. So we optimize all the inertia and the mass distance of the distance of the mass to the distribution effectively, stiffness damping, and no actuation. And we get a full Pareto front out of my 10,000 or so evaluations that come from a multi-objective optimizer. And we can see how this is colored by effective spring stiffness. And we can see how we can trade off for thrust and efficiency. Although the Pareto front is pretty narrow in this case. And then if we add actuation, we just rerun, and a day later we have the full Pareto front for the active deformation case, where we optimize not only actuation, but also these other parameters, right? And here the actuation is just simply harmonic with an amplitude and a phase. And here it's colored by the actuation power. So you see that the higher thrust cases require more actuation power, and the sort of more efficient cases are really the ones that are purely passive. They overlap here. And so what the benefit of this is that anytime I want to change some parameters to the structure or the actuation, I can rerun the optimization trivially if I put constraints or want to add nonlinear responses or time-dependent responses or change my actuation to have a regenerative sort of motor in there and use the power, we can change all of that and run the optimization on the, without further CFD. So the benefit of this is when you are in a sort of an experimental setting, you can you can always find your optimum sort of in a very rapid iteration way. So the outlook here is that I think this can unlock a very large new skill for fluid structure actuation optimization in practical applications. We still have some work to do, so I want to do further analysis of these predictions and more comparisons with CFD. When we go to higher dimensional shape parameterizations, this training approach that we use is brute force and it won't work. So we need some better way of training, which can be either active learning or I think there can be a conjunction with experiments and try to go back and forth to find iteratively, experimentally, numerically sort of optimal designs and training data to train your network to find new optimal designs. So that's something we're working on and that I'm excited about in the inverse FSI sort of part of the project. So I want to stop here. I want to thank, this is, I think the vast majority of people that were in the lab. I hope I didn't forget anyone. I highlighted in bold the people that were working on the presentation that I showed today. And so up here, the postdocs, the grad students, and my visiting students. I also want to thank my sponsors and collaborators. And I want to thank all of you for coming here. So with that, I'm happy to take questions. Thank you.
So, okay, thanks, Wim, for a very nice talk. Questions from the audience?
And in the coupled oscillation problem that we've looked at, what about if I wanted to make it not just a geometric but an actual fully elastic body?
Yeah.
Is that within?
I sort of avoided that for the simplicity. I think it's possible, but you have to have a parametric description of your deformation and then project any deformation that you get in practice on that basis. And it will just increase your parameter vector size for the shape description. But it's possible if you work from a parametric. So you can say all the natural modes of a beam or something and use that as your basis. Yeah. Yeah.
Very impressive. In your fluid structure boundary conditions, how do you handle surface tension if you want to just do some curvature on the boundary?
So we didn't do that in anything I showed. If you want to include surface tension, you'd have to reconstruct the curvature on the boundary. So that's sort of a multi-phase flow challenge. For us, you
geometrically calculate the curvature and then use that.
Yeah, we could. I think our discretization, our description of the boundary is essentially, I think I have it here. So what we have is this on the boundary when we apply the PDE. So we have a set of disconnected points with normal vectors. That's all we need to even do fourth order elasticity. And so by design, there's no topology or connectivity between these points at this stage. So if we want to use curvature, we have to go back one level up, and that's maybe these points come out of a level set field, and then we can compute the curvature from the level set and use that in a surface tension term.
The machinery is also sort of set up if you allow for density gradients and then interpret surface tension in terms of density gradients. That's a classical correlate type of machine set up to be able to do that.
If you write it as a jump, yeah. I think we can resolve the jump sharply. So if we know what the value of the jump is.
It's the other way around. You want to make it a diffuse interface.
Oh.
With a gradient and the density.
Yeah.
This is great work.
Right.
Sort of
I think,
a little bit.
yeah. Diffuse interface is maybe we're thinking about multi-phase problems and some quantities might not need to be resolved sharply, right? And then we can benefit from doing diffuse for maybe viscous terms and then sharp for like pressure terms or something like that. Yeah.
Thank you, Wim. So this is more of a philosophical question. I had asked it before in the previous presentation, 2-3 years ago, and it has to do with the two lines of work, right? On the one hand, you are pushing a lot, you are working very hard to do fourth order methods to increase improve the errors, convergence, etc. And then eventually you use that with a machine learning architecture, which essentially has no guarantees for anything, right? Even order one, perhaps.
Yeah.
So how these two worlds are, bridged with each other, or how one justifies the other?
Yeah, that's a great point. I think for the machine learning, we actually went back to the second order version of our code because, as you said, we don't need the high order. I think the high order is there's high order adaptivity. The adaptivity goes very well with machine learning because you can dial your thresholds whatever you want, and you get sort of the level of fidelity that you need. The high order IAM, if we want to go back to second order, we just change the number and recompile, and that's easy. So specifically where the high order IAM goes into play, I think is in the other line of work that I didn't show, which is our vortex dynamics sort of investigations, where we want to look more into the detailed flow structures and flow instabilities behind maybe in sort of tip vortices and things like that, where you do need to have very high fidelity near solid boundaries to find exactly how the vorticity is generated from that boundary and diffuses into the wake. And so that's where I want to apply my high order version of the code, more so than the machine learning.
Do you see any point where these two can actually work together, right? Where
I think not directly. I think to me the high order is really going for the fundamental science problems. The low order adaptivity can be for the sort of brute force training data. There's not, these are sort of separate branches.
Well, I was curious what motivated you to choose like a neural network for your surrogate in the examples you presented as opposed to something like a Gaussian process.
It's more I think the predictor that we use in that problem, it can be many other things, and we're not claiming that what we choose is the best one for the job. We had experience with the LCM, so we set them up to do this problem. We tried neural ODEs and some other things. They all sort of get something. I think the LCM was sort of the fastest to integrate in this project. But there's a whole branch of this work possible where you try to find the best neural network to get the most accurate predictions, and that's not really what I was trying to do here. Yeah. Thank you.
One more question here.
Can you say a little more about the prospects for combining the immersed interface method with LES?
Yeah, I think I'm specifically thinking about the wall model in LES, and I think we're sort of extremely well set up to do that, because if you just have a simple wall model, you need some velocity in the normal direction off of the boundary, which we can immediately get from our polynomial fit. Instead of evaluating outside, we just evaluate inside the body. And then at every control point, we evaluate a local model, right, given that information, and apply that as boundary condition locally to that control point. So in the end, everything is local to the interface. We just have to do, and the fact that we have a sort of a no-through boundary condition combined with a stress boundary condition and imposed sort of normal velocity gradients in the other two directions is also something we can immediately do. We just solve a system of equations to effectively get the DHD velocities we need to satisfy the model. So I think it's all there to essentially handle wall model LES on immersed boundaries exactly the same as on domain aligned boundaries. Yeah.
And if I may ask a last question.
Yeah.
How well you resolve the boundary layer, which is such a critical parameter, especially for unsteady flows?
get the question.
How well is this treating the boundary layer in a body, especially under unsteady conditions?
I guess the answer is how well you want, how many points you throw at it.
Do you see advantages?
I do think, yeah, the high order is sort of generically, it's still a smooth, once you extend the field, it's still a smooth field. And so I would expect high order to do better on that too.
That's the curse of the gridding, where the boundary layer has to
Right.
require such fine resolution at the surface.
Yeah. All the high order and the adaptivity both work in our favor there, I think. How well is we're always looking for more benchmark data, but once you get to these high Reynolds number 3D problems, there's very little out there.
How well in terms of cost of computation?
Yeah, but that requires having a reference. And I think at this point, we're starting to think more about experimental validations, because for the high Reynolds number moving boundary problems, there's very little sort of benchmark problems out there that we can reproduce, and let alone compare performances on. So the only thing we can compare with ourselves are code fourth and second order, but not much in benchmarks.
Okay, thank you very much.
Okay, thank you all for coming.